So last time we began discussing orthogonal projection. We defined orthogonal projection. So recall what that means is that W is a subspace of V, and this is non-degenerate on W. Okay, and then we would the orthogonal projection of projection from V to W W is the map pi from V to W defined by pi of V is W, where W in W and U in W perp are the unique elements such that V is W plus U. So that's because of non-degeneracy on W. Note that V is W direct sum W perp. This is possible. Okay, so this is. So it has the three properties. I mean, maybe other things also, which is that for all V inside V, pi of V and V minus pi of V, pi of V are orthogonal to each other. Another property is that, so in other words, we are decomposing V into two things, expressing sum of V as sum of two things which are orthogonal to each other. Then for all V in W, pi of V is V itself, and for all V in W perp, pi of V is 0. It has this property, and if we want these three properties to hold, then it is necessary that W is degenerate, because if W is not W is non-degenerate. If W is degenerate on W, I'm sorry, the form is I take it back. The form is non-degenerate on W. That's a necessary condition. If it's not satisfied, or in other words, the form is degenerate on W, then W will intersect W perp non-trivially, and for such a vector, the last two conditions will not hold. Okay? I mean, such a non-zero vector, the last two conditions will not hold. Together cannot hold. So this is just a property of orthogonal projections, and this is important in actually many applications of linear algebra, trying to find. So this also has to do with. Just as an aside, why do we care about these issues? And these are some of these things have very practical applications. Not all of which, in fact, none of which we will discuss. But as you go along, studying more things, you will realize that. I mean, there are. So just for simplicity, let us just take R2. Okay, and so this is not exactly the. Maybe this full example will make sense only after we do the whole. I mean, today's lecture. But let me nonetheless state this. Okay, so this is R2. Okay, and let us say this is W. So this is W, and this is whatever it is a form, bilinear form. Is a bilinear form, non-degenerate on W. Okay. So then suppose we have a vector. Okay. So let us, for now, simplicity, let us take the dot product itself, the form given by dot product. Okay. So then let us say that we have a vector V like this. Okay. And then when we do orthogonal projection, we will decompose it as a vector like this and a vector like this. Okay. So in this context, it is clear from the picture that this is also the shortest length line segment, okay, from V. I mean, not from V, but the end point of V. Okay. So let me, maybe I'll call this vector V. Okay. But let me just denote this point B by P. From P to the line W. Okay. So such things have, I mean, lots of applications. Not, I mean, in statistics, in numerical, I mean, calculations. Also abstractly in various notions of shortest things, etc. Okay. So it is sort of. So that's the. So that. Okay. So this idea of with respect to a form, okay, what is? I mean, how do we find projections that are orthogonal? Okay. So this is a. I mean, so this has quite a few applications. Yeah. So this is okay, one. Okay. So now let us. Okay. So let's. This is where we stopped. I mean, we stopped yesterday. That this is what we mean by an orthogonal projection. Okay. So now let us state and prove the projection formula proposition. Okay. So let be symmetric or Hermitian form on V. Okay. Again, usual convention. If V is a real vector space, we are thinking about a symmetric form. If V is a complex vector space, then we're talking about a Hermitian form. Okay. And W, subspace of V, on which this is degenerate, non-degenerate. Okay. Let W1 through WK be an orthogonal basis of W. Okay. Then the orthogonal projection pi from V to W is given by the following formula. Pi of V equals CIWI. I goes from 1 to K, where CI is the product of WI with V divided by WI with itself for 1 less than or equal to I less than or equal to K. Okay. So these are, so this is actually a very, so usually this projection, I mean, this thing will be given by some matrix form, or there will be an exact, I mean, there will be a precise algorithmic way in which we can compute this this product WI with V. Okay. or wi itself. Given any two vectors v and v prime inside v, what is v prime comma v? They will be, the way most of these problems, there will be a way that can be computed. So using that thing repeatedly, we can compute what the coefficients ci are, and then we can just immediately write down what pi v is for any v. So this is what. So before we prove this, maybe let's prove this first, and let us also observe that it is necessary that we start with an orthogonal basis of W. Okay, okay. So, and we will see it in the proof also. Okay.
Sir?
Yeah.
So for the formula for CI, does it mean what would happen if the coefficient was inner product of VWI instead of WIV? Like
It's symmetric forms, right?
No, but it's also for a Hermitian form, right? So my order
Yeah,
was
yeah.
multiple.
But Hermitian, huh? Oh, I see. Good point. It is also her. Yeah. Good point. What will happen if we take it?
No, I see we have to take the conjugate, but in the
yeah, but this is yeah. So because if you take it on the other side, you will get the conjugate, right? So then you have to conjugate it once. Then, but it's Hermitian form, so you might as well write it like this.
Okay.
Okay, let's go. Okay, let us do the proof, and then it'll become clear. See, if you okay. Yeah. Okay. So we need to make just one observation before we start with the actual calculation. Note that, so suppose we have a matrix for this form on V. Okay, so if dimension of V is n, then it will be an n by n matrix, and this maybe we don't care about. Let us say consider the matrix of the form. Consider the matrix, the k by k matrix of the form on W. Actually, we don't care about what happens. For whatever the first observation that we need to make, let us we just need to consider for W. Okay, since it is non-degenerate, okay, this matrix is invertible. Okay, so this we saw last time, that form is non-degenerate if and only if this matrix is invertible. If it's not invertible, anything on the right kernel of it will be a null vector, okay, for the form. Okay, so this matrix is invertible. Now, since this is an orthogonal basis, is an orthogonal basis, this this matrix is diagonal. Now we have an invertible matrix, diagonal, diagonal invertible matrix. So its diagonal entries are non-zero. I mean, diagonal entries. What are they? That is wi 1 less than or I less than or equal to k. These are the diagonal entries, are non-zero. Okay. So we can do this division. So we can do the division in that formula. Okay. In the given formula for the CI, we can do this division. So that's the first observation that just need. I mean, we will need to use this, but we'll see where we'll have to do the division. I mean, where in the proof we'll have to do the division, but let us make this observation to start. Okay. So now note that there exist C1 through Ck inside inside the field. I'll just call them scalars. There exist scalars C1 through Ck such that pi of v is 1 to k. This is, I mean, because pi of v is an element of W, so it can be expressed uniquely. And this k tuple is unique. Okay? K tuple C1 through Ck is unique. Okay? So this can always be expressed like this. The question is to find what their values are. Okay? That's the thing. Okay. So what we need to show is that so let
hello,
W,
sir.
yeah.
Sir, could you explain the previous part once just? I mean,
This
how
paragraph.
did we get that we can divide it?
Yeah. So what is the matrix? So we just need to know that Wi is a non-zero element, the product, right?
Yes, sir.
Yeah. So I mean, where would we see this number? That would be the diagonal entry of the matrix that represents the bilinear form on W. Right?
Yes, sir.
So we just look at that matrix. Well, the form is non-degenerate.
Oh, okay. Yes, sir. As it's non-degenerate, so we get
it's an invertible matrix. Yes.
Yes.
Okay. So let W be this thing. I'm just labeling this thing as W. Okay. What we want to show is that V minus W is perpendicular to W. So what we need to show is that V minus W is perpendicular to, I mean, it's inside W perp. Sorry, my handwriting is V minus W is perpendicular to, is inside W perp. This is what we need to show, because that's what we said, that we can write this uniquely, and once we write it, this thing will be perpendicular. So this is what we need to show. Okay, so this is what. Now, what is V minus W? And we need to check that this is perpendicular to W. Okay, so for that, we need to show that, okay, so we want to show that, V minus W is 0 for all 1 less than or equal to I less than or equal to K. This is a basis for W. W little W1 through WK is a basis for W. So if you show this, then that's what we would need to show. So let us check what this thing is. So C1 W, sorry, not W, WI, W1. The reason why we can take C, maybe I should, sorry, let me just, this is what V minus W is. Okay. We just want to expand on this, right? This, the last term. So we can take, because C is on the right side, we can take Cj outside. And by linearity, we can take the summation sign outside. Then Cj is on the second side. I mean, we are expanding on the second side, so right side. So we can take that outside. And then this is J from 1 to K. Okay, and there is okay. Now this is okay, yeah. So this is WIV minus. Okay. If J is different from I, Vj Wi Wj is 0. That's where the orthogonality is used. Okay. So then this is just Ci Wi Wj. Wi Wi. Okay. This is but that's what we had decided. This is 0. That's how we define Ci, right? So if Ci satisfies the formula, if Ci is as given, the proposition. Okay. I mean, the condition that Ci needs to satisfy is exactly this one. Okay. And now that one said, I mean, so therefore, to find the value of Ci, this has to be equated to 0. Then you have to divide by, and Ci equals this thing, this product Wiv product divided by the Wi, and that is just so that's where we are actually divide. Is this clear? Sorry, it's written in a slightly roundabout way, but I hope the proof is clear. I mean, what we showed is that with these values of Ci, this is indeed the orthogonal projection. But there can only be one set of coefficients which will make it the orthogonal projection. So, and therefore these are there. So this is the proof. So just so the person who asked me about why not take V on the left side, is it clear?
Yes. So it's just simpler to take a linear thing instead of conjugate linear. Is that
No, it is not. You have to do you can right. Okay, so I'm just, suppose we took V on, so this is just an aside. Maybe I'll just call it remarks because I want to add another remark. Remarks 1. If we tried, it is not, no, you have to do complex conjugation twice. And so you'll not, I mean, you will get back to the same thing, but you still have to do it. Okay. If you try this, okay, then we would get then this final expression here. The problem is I mean, whatever we do, it will be while calculating this that we would need to be concerned. Okay, then we would do instead. So then V minus W Wi. This is what we will have to do. Okay, so this is V Wi minus minus Cj. Then we would need to do the following. Sorry, this is slightly. Okay. Cj Wj Wi. Now, sorry, I hope it comes out correct. Sorry, so V minus Wi, yeah. So we'll get Ci minus Ci bar, and this is, I mean, Ci bar. I mean, you get this. There will be an issue with the conjugation. Okay. So this will not work. So this does not work. I'm sorry. You have to reread this comment to understand why. Okay. Because from this side you will get Cj bar. I mean, but they won't contribute because Wi Wj is 0 unless j is equal to I. In which case you get Ci bar. So this is what we'll get on the right side, not Ci minus Ci bar. Okay. Therefore, instead we should take Ci to be V Wi bar divided by Wi Wi. Okay. But this is the same as so that is the, so if you try on the other side for I mean in the complex Hermitian case, then this formula, I mean this formula won't work. To make this work, we'll have to put a bar here, then it'll work. This calculation will go through. There won't be an issue. Okay, but then it's just this one. So that's the reason why this is. So that's the first remark. Okay. The second remark is that we do need an orthogonal basis of W. Okay. Otherwise, otherwise this formula won't work because there could be some W. Okay, so otherwise, say W2 is not perpendicular to W1. Okay, so we have a basis for W, and in which the second one is not perpendicular to the first one. Okay, so suppose this is the case. Okay, so then if you apply pi to W2, we will get a formula which says W1, W2. So now we are looking for the coefficient of W1 times W1 plus W2, 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 W2.
Sir, so what are we actually trying to satisfy? I mean,
I'm telling you that the formula won't work unless we start with an orthogonal basis.
oh, okay, sir.
Yeah. That's, yeah, just give me a minute. So then we will have some dot, dot, dot. So we are doing pi of v. So pi of v is the coefficient for wi is wi w2 divided by wi times wi, right? This is what the formula is. So I'm just writing down the first two terms in this formula. That's what I've done. Okay? But this is something non-zero times w1, because w2 is not perpendicular to w1, plus w2 plus something, and this is not correct. Okay, so for this formula to actually give a projection map and the answer be correct, it is necessary that we take an orthogonal basis for w. Okay, this is an easy calculation which says that needs to be the case. Okay, so just two remarks about the statement, the formula, and so let's do an example. So let us say, so consider R2 with the usual, with the standard symmetric form. That is the one that coming from dot product. Okay, so let W be the span. So now there is a notational issue. Previously, I was using this angle brackets to denote span, but if there are two vectors, when I put angle brackets around them, it would be very ambiguous whether I mean a product or the span. So I'll just write span. Okay. Span of, I mean, right now I'm only using one vector, but so this is like the picture that we had drawn. So this is R2, and this is W, okay, the span of 1, 1. And so let us say that, okay, so let V be a vector AB inside R2. Then if we project V, what is the coefficient that we would get? Okay. So let us just call this vector W. There's only one. W has length, I mean, dot is equal to 2. Okay, this is, it's not length, it's square, but 2. And V dot W is just A plus B. So the projection would be, so therefore pi of V is A plus B divided by 2. This is just a real number times times W. Okay. So this is the projection. And yeah, so if A and B are both positive, then the projection will be some, and yeah, that is, this is what that means. So although we stated this thing, the proposition only for a subspace, it is still applicable to work with the and also useful when we work with the whole space also. Okay. So suppose that this is non-degenerate on W, on V itself, the whole space. Again, the two cases, real symmetric or complex Hermitian. Suppose it is non-degenerate on this. So let V1 through Vn be an orthogonal basis of V. Then for all V inside V, V is, so we want to express it in terms of this basis. We can just use that formula, okay, which is the coefficient of Vi. What would that be? It would be Vi V divided by Vi Vi times times Vi, sum of these. This is just applying the previous formula. Apply proposition with V equals W. Because this is non-degenerate. No, I mean, the point that one has to note is that V is pi of V, where pi, maybe I should clarify it another way. Note that the orthogonal projection from V to itself, okay, because it's non-degenerate on this thing, is the identity map. So V equals pi of V. Okay, and this is the formula for pi of V. Okay, so that's the. Okay. So this is also, this is, so given a vector with respect to some basis, we have some new convenient orthogonal basis and express it now with respect to that. So this is also something that will come up. Okay, okay, so one typical place, in addition to statistics and application, that's the sort of applied mathematics where one sees these things. I am not making a distinction between those things. Another place where this comes up quite very naturally is when one studies functions. Okay. So you already, did you do the exercise or did I? Sorry, did I assign an exercise about some integrating to polynomials?
Is that
Did
integral
you do,
given as the bilinear form?
Yeah. Between some
okay.
definite integral of a, you that was assigned last week. Correct.
Yes.
Yeah, so that sort of things is again, so that's another place where this sort of given, so there you were considering polynomials of degree at most 2. So one natural basis for them is 1x squared for that vector space. Okay, but we may also consider other useful orthogonal bases, and people have studied, from 2-3 centuries ago onwards. Okay, so given a polynomial, how do we express it in terms of that natural basis? So that's again a question that that has lots of applications in various parts of maths. Okay, so therefore, so this sort of, this part expressing, the notion of orthogonal basis and expressing an arbitrary vector in terms of an orthogonal basis is an important topic. Let's put it that way. Okay, that is okay. Yeah. So there is an example in the book. I'll mention in the exercises. Please make sure that you read it. Another corollary. Yeah, another corollary. So let be symmetric form / Hermitian form on V, then there exists a basis V1 through Vn of V such that there exists an orthogonal basis such that the pairwise product, not pairwise, self Vi is +1, -1, or 0 for each I. So this is, this is the place where an arbitrary symmetric, let us just, okay, for now, let us just consider a symmetric form, a real form, just for the just for my remarks now. Okay. This is one place where an arbitrary real symmetric form differs from the dot product form. Okay. Dot product form is positive definite. We will not get this property, okay. But given any symmetric form, there is this thing. Okay.
If Vi is a basis element, then can it be that Vi comma Vi equal to 0?
Yeah, I mean, we haven't said what. I'm not saying it's non-degenerate. Symmetric.
Okay. Okay. Yes.
Okay. Yeah. That. In fact, that is what I was. That is what I was just last minute contrasting. That this won't happen for the dot product form, okay? Because it's positive. That's positive definite. Okay? But here it is not. For an arbitrary symmetric form, it always. This. It always. Has this property. This is all that you can guarantee. Okay? In fact, yeah. So there is a result which says the number of ones and the number of -1s, the number of zeros is independent of which basis we choose, provided it has this property. I haven't decided whether I should discuss the proof or leave it as an exercise. With some details. So I will, that I'm still debating. Anyway, I will not get to that statement today. So I will make it call on form. So the other thing we were discussing, other things. See, last week I said I will do some example, which actually sort of gives you an application why we are studying these other bilinear forms. Symmetric bilinear or Hermitian forms. So one may be this example of this polynomial, the definite integral, and that defining what was that exercise? Sorry, let me just give me a minute. Yeah, so that in that exercise you showed that integrating, or you had used the fact that integrating two polynomials, their product, some definite integral, gives a symmetric form, and then you were asked to find an orthonormal basis for that thing, right? So similarly, so another place where one sees this is, one needs to worry about this form, symmetric bilinear forms given by other matrices other than the identity matrix. The natural place where it comes up is multivariable calculus, specifically manifolds, okay, and what is called the tangent spaces, the map between tangent spaces. So I tried to work out an example. I realized that I will have to spend a lot of time doing that example to make any sense. It'll become clear to you after you do your first calculus class. First multivariable calculus in your third semester. Once you finish that course, the idea of a tangent space, if you have a diffeomorphism, it induces a map on the tangent spaces, etc. But till that is done, and then you talk about some metrics on the tangent space, etc. Till that is done, I will not be able to justify this example in any concrete sense. So I will tone down the example and I will put them as exercises. Some very special cases of those examples. Okay, so this, I will do that. So at least you'll see some other. At least you will have some inkling of an idea where else this sort of things that we study the forms given by some real symmetric matrix, or the Hermitian form given by a Hermitian matrix, etc., come up. The example I give you will be for real, but similar things can be discussed for complex also. So I will put a sort of a very toned down example in the next round of exercises. So this is, I was planning to lecture on it, but I realized that once I started writing out some notes, I realized that this, it is little advanced. And this is probably, right now is probably not the appropriate time to worry about all the details of that example. So it is better to understand some smaller example, at least to have an idea that these things will come up later. Okay, so sorry, I got distracted. Now what is the statement? Yeah, correct. So this is a, okay. So proof. Okay. So we know already that there exists orthogonal basis. Okay, so we have already shown that V has an orthogonal basis. This we did in the last class. Okay, so call it V1 through Vn. So now we look at the okay, so so now what else are we asserting? We are asserting that some statement about the length or the self, I mean Vi, the product Vi. I should not use the word length. I'm just using it informally as what it would matter, what it would be, or the length squared if we were discussing dot product. So informally, in that sense, I'm talking about length, but one should not refer to this as length. Okay, but I'm just okay. So this is what we need to know. What is this Vi? Vi. Okay. So this thing is always a real number. Okay. That is right in the real case, of course, and in the Hermitian case, by definition, it is a real number. Okay. So this is okay. So if we multiply yeah, so we want to adjust the length to +1 -1 or okay. So sorry, I'm using okay. Okay. So if this is 0, then we don't need to do anything. Okay. So if is 0, then there is no need to do anything. So of course we are going to just so the conclusion. I mean, we have an orthogonal basis. We need individual vectors to have some other property in it. No pairwise. I mean, the extra condition that we need depends for each I independently. It's not about pairs, so we can just work with one vector at a time. Okay, so there is nothing else to do. Nothing to be done. Okay, for that I mean, let. Okay, so I'm just going to individually modify V1, V2, V3, etc. And I'm just going to describe done. I mean, done to Vi. If is positive, then we can take a square root. Then let so then we want to divide by the square root of this number so that this will become 1. we want to replace V, we want to divide Vi by the square root of this number. Okay. So then let C inside R be such that C square is VI. I either take the positive one or negative one, it doesn't matter. Okay, but the point is, you can take a real number, this property. Okay, then Vi divided by C, Vi divided by C is 1. Okay. Replace Vi by Vi divided by C. Okay. Okay, so this is just, I mean, in the concrete case, if you're discussing with dot product, okay, what we have done is replace that vector Vi by the unit vector in that direction. That's what we've done. Divide by its length. That's what. Okay. So, but of course, it has been written like this because we do not. We don't. Right. So then, if Vi is less than 0, then let C in R be such that C square is minus Vi. Then Vi divided by C, Vi, the product is minus 1. So replace Vi by Vi divided by C. So this proves the that statement. Okay. We can rewrite this. So I hope the idea is clear. I mean, in the dot product situation, what we are doing is, given an orthogonal basis, we just take each vector and just divide by its length, so that now it's orthogonal and of unit length. It's the same argument that we are doing here, except we don't think of this Vi as length, because at least length by this could be 0, or I mean Vi could be perpendicular to itself, and this product could be 0, or it could be negative. Okay, so this is okay. So this is the this is what.
Hello, sir.
Yeah.
Sir, if it is a Hermitian form, then how do we know that Vi will
That's a
always
that is the
be
definition
real?
of Hermitian. I mean, that follows from the definition, right? Means Hermitian. Hermitian says that this is.
Oh, yes, sir. They're the diagonal elements.
Yeah, well, okay, we haven't given a matrix, but Hermitian says that this is.
Yes, sir. I mean, the conjugates are same.
Correct. Yeah, so if you put it the same thing, it must be real. Right. Yeah. So in terms of matrices, the above corollary can be stated as follows. Let A be a real, symmetric, or complex Hermitian matrix. It will be an n by n, let's say. Then there exists an invertible matrix P, n by n, P, such that I'll just write P star AP, because if it's so I okay, yeah, actually it does matter whether it's. I'll be sorry, maybe I should be clear. Then there exists an invertible n by n real matrix. Okay, so respectively complex, P, such that P transpose AP, respectively, P star AP. So if you're discussing real symmetric matrices, we can take P to be real. That's what I want to emphasize. Is of the form is diagonal, is a diagonal matrix. Matrix with ones, -1, and 0 on the diagonal. I mean, or with only ones, -1, and 0 on the diagonal. I'm not saying all three of them have to occur, because of course take the identity matrix, okay? But whatever occurs will be a subset of this. That's what this thing says. So now I want to define a thing called signature. Yeah, maybe. So by this corollary, so let P trans, I mean AP or P star AP as the case be. Okay. Be of the form. I mean, this is right in the form some. So this is the plus ones. So I'll just call it I. So I mean, I'll just follow Artin's notation. This is too small. Okay. P by P identity matrix, which means these are the ones. Then M by M minus identity matrix. So these are the minus ones. And then okay, so 0 sub Z. And anyway, these are zeros here. So we can all, that's what the thing says. I mean, after rearranging some basis vectors, so one will always look, one can always make the ones appear first and then the minus ones and then the zeros. So one can always write like this, where P is the number of ones, M is the number of minus ones, and Z is the number of zeros. Okay. So one can always write like this. In a suitable basis, every symmetric symmetric real form or complex Hermitian form looks like this. That is what we have established so far. And I mean, in a suitable basis. And P plus M plus Z is equal to the dimension of the space. And the form is degenerate, non-degenerate. If and only if Z is 0. Degenerate on V only if Z is 0. Okay. That means when you express it, okay, there is no. Okay. And the pair P comma M, that is a number of plus ones and the number of followed by the number of minus ones. Okay. This is called the signature of the form. Okay. So of course we call it signature of the signature of the form. So it is somehow uniquely associated to it, not depending on the basis we chose or the matrix P that we chose. Okay, so that's the part that I will, I think it can be done as an exercise. Let me think through it. If it's not doable as an exercise, I will do it in the next lecture. Okay. So that the signature, I mean, this, the number of P's and the number of M's that we will see, and therefore also the number of zeros. I mean, sorry, the number P, M, and Z, these three numbers does not depend on the choice of bases. Or in other words, the number of ones, the number of minus ones, the number of zeros on the diagonal is independent of the choice of bases. Is a fact. I think you should be able to do this an exercise. Let me think through it, and I will outline the steps anyway. But if there is some technicality, I will discuss it in the next lecture. Okay. So this is called the signature, and we can make a few more remarks. The form is positive definite.
In computation of determinants last semester, we also came across signature. So is this signature anyway related to that signature?
No, that is a signature of a permutation, right?
Yes. Oh, okay.
And
does it matches for the bilinear forms matrix?
No. The word signature was not associated with a matrix. It was associated with a permutation, right?
Okay, yes.
I mean, typically the context of determinant, the signature is associated to the permutation, which depends, which says in which row, which column you have to pick those elements.
Yes.
Am I right? Is that, yeah.
Yes.
So
yes.
no, they are not. They're just the same word used in.
Okay.
Yeah.
Okay.
That signature we will see. Sorry. Actually, I had not hoped to spend so many lectures on linear algebra. I had hoped to begin group theory by this time, but things slipped. I mean, so anyway, that signature we will see when we start discussing groups, or at least permutation groups, but not this one. I mean, that's not this. The form is positive definite if M and Z are 0. That means there are no minus ones and zeros in the diagonal. Okay. Positive semi-definite okay. If M is 0, okay. And I mean if and only if 0, and so on. Negative definite, negative definite means there'll be no plus ones and zeros. Negative semi-definite will be there'll be no plus ones, and indefinite would mean that there'll be both pluses and minus. There will be at least one plus one and at least minus one minus one. Okay. So there was one form that we had already seen, Lorentz form.
Sir, what did you write the condition for semi-definite?
M is 0. There are no negative ones.
Okay.
So this one has signature 3-1. And so when we say signature, we only mean the plus ones and minus ones. Of course, the number of zeros can easily be determined by this formula. We know what dimension we are discussing. So if P plus M doesn't add up to the dimension, then it means that the remaining things are zeros. Okay. But here, yeah. So this is just a. Yeah, so there is one. So there's one leftover business from an earlier section, which is that what are the symmetric bilinear forms that are equivalent to the dot product in some basis. Okay. So I said I will do it after we discuss further things. So this is an appropriate time to discuss it, but I think I will just. I mean, it'll take me some 15 minutes to discuss it. So that thing I will I postpone it to the next lecture. But I just finished this. Just one more point about that comes up when we discuss this orthogonal basis, orthonormal basis, etc. So I will do that. Called Gram-Schmidt. Maybe this you did last. Did you discuss?
I think only for inner products.
Only for what?
Inner products. Yeah, like positive definite. Yeah, dot products.
Yeah, okay. Only for dot product. Okay, is it okay? Yeah, but only for dot product or all positive definite? Anyway, let me just do it. Anyway, so in 5 minutes I will do this because in Gram-Schmidt orthonormalization. Okay, so what we want is to build a basis. Okay, so aim given a basis V1 through Vn of V and a positive definite form. Okay, so again, I'm being sloppy as to is it a real symmetric form or a complex Hermitian form, but the statement applies in both situations. Okay, so you can apply it positive definite form on V. Okay, find an orthonormal basis. Convert this thing to an orthonormal basis, something like that. Orthonormal basis of V. So I'll just describe it algorithmically. I will not. Okay. So this is I think you, if I remember right from my conversation with Professor Ramdas, he did discuss some variation of. I don't remember if he said only for dot product or for all positive definite, but let me just do it.
So I think we did it in general.
But technically only for real, but it's the same argument for complex also. Yes. But it's okay. I will just in 5 minutes I will just state this and I'll be done with for today. Yeah. So what do we do? Yes. So we start like this. We start with W1 to be V. So let W1 be V1 itself. Okay. So now we need to construct a W W2 such that together with W1 and W2, it would span V1 and V2. And W2 is perpendicular to V2 to W1. So this is what we want in the second. Now. So how do we do this? We take the projection of W2 again against W1, and then take the difference. That would satisfy these two conditions. Okay? Projection of V2. Okay? So we do the following, which is that W2 is V2 minus. So we want to project V2 against the space that we have already constructed, which is span of V1, span of W1. Okay. So now, first of all, V2 is in the span of W1 and W2. Okay, and V1 is anyways in the span of W1. So the span condition is now checked, and W2 is perpendicular to W1. That's because we are just W2 is the complement. We have just subtracted from V2 its projection to the space being spanned by W1. Okay, so this is what this will work. Okay. So next step we want. So now it's better to introduce some notation. So let W2 be the span of W1, W2. Okay. So next we want a W3 such that span of W1, W2, W3 is the span. Of course, we could have just said let W2 be a span of V1, V2 also. Okay. And so this is W3, and W3 is orthogonal to this whole space W2. Okay, so this is what, of course, we need to, I'm sorry, this is not it. Okay, so I will summarize. This one comment needs to be added at the end, which I will do. Okay, so what do? So we do this. We take W3 to be V3 minus the projection onto the space W2, orthogonal projection onto the space W2. And that is possible because W2 already has been given a basis which is orthogonal. Okay. So this is W1 V3 divided by W1 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 minus plus W1 W2 V3 divided by W2 W2 W2. So this is whatever in the brackets is the projection of V3 onto the space W2, and that we have removed. So now we get something that's orthogonal to this projection. Okay, so this is this is what will work, and so on. Okay. So what we have now constructed is that W1, W2 up to Wn is an orthogonal basis. Orthogonal basis of B. Okay, and since so far we have not used positive definiteness anywhere. Okay, where we will use that is that since the form is so replace Wi by Wi divided by the square root of this thing, okay, to get an orthonormal basis.
So didn't we already use positive definiteness
here? Where did we use positive definite earlier?
So for the denominators, Wi, W.
No, that just requires non-zeroness, right?
Oh, gotcha.
Yeah,
Yes.
that, I mean, the orthogonal projection works for all non-degenerate forms. You don't need a, but of course, see, we're doing this sort of incrementally. So to maybe, yeah, so yeah, so okay, so maybe, yeah, see, so question is, what is our quantifiers, right? Are we saying that we can start from any given basis and do this? Okay. Then yes, most likely we would need a positive definite form, because if it's not positive definite, we can probably find some basis where this argument would not work. I mean, where the argument up to this stage also won't work. Because you remember, to apply the orthogonal thing, you need that subspace. I mean, to project onto a space, you need a condition that on that subspace, the form is non-degenerate. If it is positive definite, you get that for free for all subspaces. But if it's indefinite, then you could badly choose a V1 through Vn, and then this argument. Forget about making them unit length, but even the previous step might fail, because I mean, the first statement that we, this thing, projection formula, W a subspace of V on which the form is non-degenerate. Okay. So this we need, if you go back to the proof, or at every stage of this argument. Right. On this W2, then W3. I mean, so maybe I should just, this is a good time to remark here. I mean, the way this will work, Wi is the span of V1 through Vi. So we want the form to be non-degenerate on this. So it depends on, I mean, if you choose same form, if you choose a different basis, will the algorithm get stuck? Yeah, it might. But yeah, so that is, but if it's positive definite, it is not going to get stuck anywhere, irrespective of, yeah, so the way this is written like this, that this will work for any given basis and any, this will work. One has sort of implicitly used positive definite. But yeah. Basis. I'll stop here. So yeah, so on Thursday I will just do this a little bit of some leftover material from an earlier section. What are the things that are equivalent to dot product, and then just a small discussion about and then we'll start spectral theorem. That's a crucial topic in the study of these forms. Okay, so that we will do, and then we will stop these bilinear forms for now and start doing group theory. So yeah, that's the plan.
Hello, sir.
Yeah.
Sir, if we had negative definiteness here, then we could have adjusted it accordingly, right? I mean,
yes, not that far. We have to. I mean, you have to do some adjustment. Yes.
Yes, sir. But the indefiniteness or semi-definiteness causes trouble. Other than that,
correct. Yeah. Indefinite and semi-definite. If it's indefinite, then you might start with some wrong choice of initial basis, which might get stuck after some time.
Yes.